Finding the domain of a rational function. Here we have 3 plus 5x all over 2. When you're looking for the domain, what you want to focus on is the bottom, the denominator of a fraction. And you want to make sure that the denominator does not equal 0. So if it's a regular number, just a plain number, there's no variable in there, you don't have to worry about it. Our variable, x, can be any number. So how we would write that answer in set notation is the set of all x's such that x is a real number comma, well, we don't need any comma because there's nothing else other than that. It can be any real number. So then we close out our set notation. Looking over at this one, we do not want the denominator to be 0, so my denominator is t. So that means that t cannot be 0. Writing this in set notation, we have the set of all numbers t such that t is a real number and t does not equal 0, and close my set notation. The comma in between the different things is saying that it has to match this condition and it has to match that condition. The bar, the pipe, is saying it's worded as such that, or where, or when. Those are the words that we use to say the pipe. And it means there are conditions to this variable being in the set. The conditions are t has to be a real number and t cannot equal 0. Looking down here at this one, again, we don't want the denominator to equal 0. It's not that x can't equal 0, it's that the entire denominator cannot equal 0. So I want to take this denominator, and I want to say it does not equal 0. So I'm going to completely ignore the top, and I look only at the bottom. And I treat this like that's my equation that I have to solve. So just like any other problem you're solving, we add the 1 over. Now we have 4x cannot equal 1. We divide the 4 out. So 4's cancel 4. I'm left with just the x there. So I have x cannot equal 1/4. And then I want to write that in set notation. So that's going to be the set of all x's, the set of x's such that x is a real number and x cannot equal 1/4. And then I close my set notation. So these 3 are fairly easy. That last one, though, is going to take a little work, so I need a little bit more space. So I'm looking again only at the denominator. That denominator down there cannot equal 0. So this cannot equal 0. I'm only looking at that. The problem with this is I have a quadratic. So I have to factor that. I have to solve this as though it were a quadratic that does equal 0. But I'm going to keep the does not equal sign there. So I take my x squared minus x minus 12 does not equal 0. I identify my a, b, and c. A is 1, b is negative 1, c is negative 12. I'm out of benefit here because a is equal to 1, so I can use a shortcut. I see that c is negative, so because it's negative, I know my signs are different. I see that b is negative, so that tells me that the larger number is going to be negative. So now I'm taking my a times c, so 1 times negative 12. Gives me negative 12, and I factor that. It could be 1 times 12, could be 2 times 6, could be 3 times 4. I know that my larger number is negative, and I see that 3 minus 4 is 1, so I'm going to use the 3 and the 4. It's 3 and negative 4. So using my shortcut, I now get x plus 3 and x minus 4 does not equal 0. So just like when we were working with them where they did equal 0, we split it up into the two parts and say that does not equal 0 and that does not equal 0. What are my two possible answers? So I'm going to split it up like that. Subtract the 3. I get negative 3 cannot be x. Add the 4. I get x cannot be 4. Now I need to write my set notation. I already know my two answers. And I know that there are two answers because my exponent is 2. So, two answers. So I have my set notation, x, such that there are conditions that apply. X has to be a real number. X is a real number. There's another condition. X cannot equal negative 3. X equal not negative 3. There's a third condition here. X cannot equal 4, comma, x equal not 4. And that's the end of my conditions, so I close my set notation. And this is my domain. And that is finished.